Right, now let's get into the experiments. I mentioned this before when we were talking about experiments, but we want to get into it in a little more detail. When it comes to experiments, we want to make sure that our experiment is tightly drawn in. We only want to change one thing, because if we change 2, 3, 4, 5 things in our experiment, we're not going to be able to tease apart which one of those things is actually causing any sort of difference in the results we get. So we call that experimental condition a treatment, and we apply that treatment to our experimental group. So, for example, if we're talking about our plant example that we've been talking about, our experimental group would be the group who received fertilizer, and the treatment would be a certain amount of fertilizer. But that's not enough, because we want to know if fertilizer positively affects plant growth and causes them to grow more. Well, how do we know what baseline growth looks like? We need a second group called a control group. They do not receive the treatment, and they can serve as a baseline so that we know and we can compare results against our baseline. So let's look at our plant thing again. We have our plants in the experimental group that have received fertilizer, and our control group receives no fertilizer. That way, we don't look at any growth as the fertilizer is causing that growth. We know that without fertilizers, plants grow this much, and if we add the fertilizers, they grow this much more beyond the normal growth rate. So we can compare our fertilizer plants against the non-fertilizer plants and see if there's a difference in how much those plants grow. The variables are the parts of an experiment we change. So in this case, we're changing how much fertilizer, how many nutrients are available to our plants. Additionally, we want to make sure we control for other factors. So in our plant example, we want to make sure that the only thing that's different between the control group and our experimental group is the amount of fertilizer. We want to make sure that both groups are getting the same amount of light, water, that they're the same species of plant, that they have the same type of soil before we start changing things. Because again, if you give your control group very little water and your experimental group a lot of water, and you give your experimental group fertilizer and the control group gets none, that difference, when you get to the end of your experiment, you're not going to know if it was the fertilizer or the water that caused that change. By controlling for the water and making sure that all plants get the same watering schedule, you can eliminate that from your list of factors that are causing any sort of change in your results between your two groups. Now, that being said, we are humans, and humans carry bias. Biases are beliefs that are not necessarily backed by facts, and they can influence results or our interpretation of the results. And because we're people, we're human beings, these are often subconscious. It takes a lot of introspection and a lot of internal work to identify your own biases. You don't want to be hoping for a certain result and then either A, design your experiment to try to favor that result, or misinterpret the data to support that as well. You want to try to be unbiased as possible. That's really difficult, and so you really have to do some internal thinking about yourself and about what you want and what sort of beliefs you have before going into your experiment, before going into even all the way to the observation hypothesis stage. Think about those things about yourself. Because if you don't eliminate those biases, you can skew your results and you can skew the data to favor something, and you might not even realize you're doing it. It's also important that all these experiments can be replicated, meaning that someone else can come in, do the same experiment, and get relatively the same results, right? So we repeat a study, which is honestly best done by competitors, those who have reason to not necessarily support what you found, because if they find the same results, that adds power to the results then. It increases our confidence that these results are sound and accurate. And it helps us determine what's actually responsible for the results. So you want other people to do the same experiment and come to about the same conclusions. The numbers don't have to be exactly the same, but they should be similar enough that the conclusions remain the same. Now, once we've gathered all that information, how do we make sense of it for other people? Some of the best ways to display data that we collect are visual displays. It's a lot easier to understand. You can pack a lot of information into a relatively small and easy to digest format. And there's a few different ways we can display data. These are some of the common ones. The bar graph, which is just rectangular bars that show the data. So let's say we have our plants, like plants A through D that got no fertilizer, and E through G that got fertilizer, and we show how tall they were at the end of the experiment. That could be one thing we do. Or a pie chart where we show slices. That probably wouldn't apply to our example right now, but it could apply to some other sort of experiment where we're showing proportionate data. Or a line graph, a line or a curve that connects data points to show trends across many data points. So we could, for example, if we're using our plant one, we could have our average daily growth rate for our control group and the average daily growth rate of our fertilizer group, and show how that growth changes over time for the entire group. So we'd only have 2 lines instead of a bar for every single individual plant. So there's many different ways that you can display that data in a very easy to digest manner. Which one you use is going to depend on your experiment and kind of what your data looks like and how much data you have. Again, you wouldn't use a bar graph if you had 100 plants and you wouldn't show every single individual plant. In that case, if you have 100 plants, you might just show the average of the 2 groups together and just show 2 lines in a line graph. Let's kind of tease apart one of these and look at our visual display. So anytime we look at some sort of visual display of data, there's some common things we're gonna notice. And these are things that we want to notice as readers as well. Everything should have a title. We need to make sense of it. We need to know, well, what is this even representing? So in this case, effect of study time on exam performance. So how much of an effect does the amount of time you spend studying have on your exam score? We have the y-axis here, performance on midterm exams, so what score did these people get? And this is always going to be a dependent variable, or almost always is a dependent variable, which is down here. Basically, we have no control over, like, we're not going to change these numbers. These numbers, the scores, are dependent on the study time. So we can change how much someone spends studying, how much time they spend on when they study, but this line here, these numbers here, are reliant on this factor here. So we call it the dependent variable because it's dependent on something else. In this case, exam performance is our dependent variable, and it is dependent on how much time someone spends studying. These individual dots are the data points. They're individual measurements. The x-axis, this is our independent variable because we can control this. This is something, right, that we can observe. We can change it as required. So we can say, hey, group A, you're going to study 1 hour. Group B studies 2. C studies 3. D studies 4. And group E studies 5 hours. But the scores are dependent on how much time, right? So we tell this group, all right, you're going to study for 1 hour. They do that. They take the exam. They get the score. This group is told you're studying for 2 hours. They study for 2 hours. They take the test. They get a score. So in general, our x-axis is going to be our independent variable because that's something that we're controlling. We're saying study this many hours a day, or we're saying we're going to add X amount of fertilizer. Versus the dependent variable, which relies on whatever's happening down here. So getting a good score on the exam depends on how much time you spent, or how much, if we're talking about our plant thing again, how much fertilizer did you get? If you got a lot of fertilizer, right, that can affect your growth at a certain rate, versus if you don't get fertilizer, you get very little fertilizer, how does that change that? Once we have that data, we want to use statistics to help us make decisions to determine mathematically how different things are. Now, it's not a perfect world, and if we're doing something like our plant fertilizer experiment, every single plant that gets fertilizer isn't necessarily going to grow this at the same rate or the same amount, and same thing for our controls. There's going to be a little bit of variance, a little bit of differences between the individual plants. So how do we know if something is what we call statistically significant? Meaning that the differences that we see between our groups, like our fertilizer group and our control group, are significant enough to say that this is not due to random chance. Because sometimes that can happen. There's going to be some natural variation no matter what we do. But we just need to separate out if that variation is due to just pure luck, or is it because something is significantly changing these groups or making these groups different from each other. Now, it's important to know that correlation does not always equal causation. So a lot of times you'll see a study that says X is correlated with Y. So we know that there's a relationship between the two, but based on the studies that we did and the information we have so far, we can't necessarily make a causation statement. We can't say X causes Y yet. Maybe later down the road, if more evidence is collected or if stronger evidence is found or new technology or techniques come out, we might be able to make that sort of statement. But it's not a problem to say that there's a correlation rather than a causation. And a lot of times, sometimes you want to play it safe and rely on the correlation part, not the causation part. So for example, here's some funny examples that show that correlation is not always equal to causation. So for example, there is a pretty strong correlation between people who drowned by falling into a pool and films that Nicolas Cage appeared in. Now, does Nicolas Cage being an actor in movies cause people to drown? No, that would be pretty nuts. Or if we look at the divorce rate in Maine and per capita consumption of margarine, it's safe to say that margarine is not causing people to get divorced in Maine, nor is divorce causing an increase or decrease in margarine consumption. So if you think about it, those are very silly examples, but there's some really tight correlations there. So you want to make sure you know the difference between the two, because there are instances like Nicolas Cage and pool deaths that clearly don't have a link together in terms of causation. It's just the data happens to fall where it falls.